Good morning, good afternoon, and good evening. My name is Viral Vigila, and I'm here with our presenters Ted Huang and Angela Criswell.
Hi, everyone.
Hello.
We are closing off our 2024 webinar series on additive manufacturing. This will be the 11th episode in the long-running webinar series for X-ray computed tomography for materials and life sciences. But before we begin, a few housekeeping items. As far as today goes, as usual, we'll be taking your questions during the live webinar. We ask that you submit the questions via the Q&A button on your screen. We will not be monitoring the raise hand or chat feature. However, I will be sharing some relevant links in the chat window, so be sure to check it out. At different times, we will be stopping in the webinar and taking your questions and answering your questions live. If any questions are unanswered, we'll respond to you once the webinar is completed. If you have difficulty viewing the webinar live, it is being recorded and a recorded link should be available beginning tomorrow. With that said, let's get started.
All right. Thank you so much, Vero, and thank you so much for everyone tuning in to the webinar today. My name is Ted Huang. I am an X-ray imaging application scientist here at Rigaku. And today the webinar is additive manufacturing in X-ray computed tomography. And throughout the webinar today, we're going to cover the topics about the first one, what is additive manufacturing? For those of you, if you're not too familiar with additive manufacturing, this should bring you up to speed. And for the people who are already very well versed with additive manufacturing, going through these basics again with me is a good way so that I can introduce you to the second point I would like to bring out today, is why structure analysis is very vital to all additive manufacturing processes. And with that, I would like to tell you what is X-ray CT, so that to convince you, X-ray CT is a tool that's going to be very helpful for additive manufacturing and why you would like to use it or want to introduce it to your arsenal that you're already using it. Now, the last point I would like to make today is to show you actual examples. So that's the most convincing, to show you actual examples of additive manufacturing product analyzed using X-ray CT. So without further ado, let's go to the first point, additive manufacturing. So what exactly is additive manufacturing? This term has been coined quite early on, and initially it was only a prototyping tool. So initially the definition was a prototype model generated using CAD, meaning computer assisted drawing, to be fabricated directly without process planning, meaning you don't have to worry about making the molds and calculate the throughput. You just design it and then you have a way to build it. But as all we know, throughout time, it has been developed. Now this technique is more than just prototyping. It can be used to make actual product. But with that, some increased complexity. So there are going to be some process planning involved, but it's still not as excessive as many of the traditional manufacturing process. So how many additive manufacturing process out there? According to ASTM standard, there are seven major types. The first one is vat polymerization. So you have a vat of the liquid that then you photopolymerize in using UV ray or some other light source. So we can produce polymer additive manufactured product in this way. The second very common one is powder bed fusion, PBF. You have a bed of metallic powders and then you fuse them layer by layer using a heat source, either a laser or in some cases electron beams. Next one is binder jetting. It's kind of like the powder bed fusion, but for non-metallic powder. You're not fusing them using heat. It can be using binders or some other techniques. Next one is material jetting. So contrary to having a predetermined bed of materials, in this one, you can decide what type of material to put where and using different curing methods or binders. So you have a higher degree of freedom in terms of making your material out this way. Next one is sheet lamination. This is most commonly used for ceramic type additive manufacturing. So cut it into different sheets, lay them on top of each other, and then later put them into furnace for sintering. And then next one is material extrusion. This is probably the most common additive manufacturing when people think about a lot of commercially available equipment you can even buy to put it at your house. You just extrude the materials out and layer by layer, put them together into the product you want. And the last one, direct energy deposition, DED, it's kind of like material jetting, but for metallic powders. You throw out your metallic powder at the same time with the heat source trying to fuse it, giving you a high degree of freedom to craft the product you want. And there's a last term, it's kind of like an umbrella type to categorize and incorporate all type of additive manufacturing you might develop, but that is not strictly fitting into all 7 categories beforehand. And by the way, all these nice figures, I would like to give credit to Dr. Trumbull back at Purdue University. These are taken directly out of the slides when I was taking courses back at Purdue. So looking at all those type of different printing process, you might think, oh, they're so different. But there's a reason they're all called additive manufacturing, and the reason why people love it is quite similar. The first one is fast. I'm not talking about the build time for individual parts, because you cannot be faster than extrusion method using a conventional mold technique. I'm talking about the design to product time. So because without excessive process planning, you just design it and then you can just build it. You don't have to go through all those tedious process. And with this also comes a fast iteration cycle, meaning you can make your product really fast and then immediately learn how to improve on it and make the new batch or new version a better one. Another factor is form. Because of the degree of freedom additive manufacturing provides, there are many complex shapes that conventional manufacturing techniques are simply impossible or impractical to make. Now you have access to them. And lastly, as you just saw, there are a mass amount of material choices you can use using different type of additive manufacturing process. So with that, I would like to go to the first poll question to ask every one of you some questions. With that, I would like to hand it over to Angela.
Hi, everyone. So I'm going to launch our first poll question for the day. You should see it in front of you. Now you can answer, you can select multiple answers in this. So we'd like to know, which additive manufacturing material system are you most interested in? Are you interested in polymer or perhaps metal? Maybe ceramic is what you're interested in. Or maybe you're using hybrid materials. Or maybe there's something else completely. And if you do answer other, I would encourage you to put that specific other material in the chat so we can learn a little bit about what you're doing as well. So it looks like we've got about 70% of the people are participating so far. So I'm just going to give a few more seconds, 3, 2, 1, and I'm going to end this poll. And I'm going to share the results with all of you. And it looks like, Ted, 63% are doing metal, the most predominant one, followed by polymer at 47%, ceramic at 31%, and hybrid at 13%. So metal's the clear winner here. So I'm going to stop sharing, and I'm going to send it back to you.
All right. Thank you, Angela. And also thank you, everyone, for voting in the poll to let us know what kind of material system you're interested in or already working on. So as we're seeing here, the metal seems to be very popular, but also polymer and ceramics are also a lot of people using additive manufacturing. It's also corresponding to our experience working on these type of samples. And I would be happy to inform you, no matter which system you voted, you will be able to see some of the examples throughout today's webinar using X-ray CT. So let's move on to the webinar again. Okay. So different types of systems, material systems, or additive manufacturing processes. But again, I would like to bring attention to the common cause of using additive manufacturing. Like when you're doing additive manufacturing research, what exactly is the point you want to look at? What is your interest? So there are many types. The first one is probably improve overall properties. If the stuff you're building is working well, it has good properties, that's always better. If it doesn't, you have to find a way to improve it. So you're looking at the properties perhaps. Or you could be looking at the structures. You want to print out a thin pillar, you don't want it to be too thick. You want to print out a circle, you don't want it to be a cube. So you're maybe refining the structure, you're printing throughout your process. Or you're focusing on the after processing, after printing, maybe for example, the ceramics, you want to know the sintering process, how to fine tune it to achieve the best outcome that you're looking for. And obviously, all three of these combined is the reason why today additive manufacturing is no longer just a prototyping tool, but a proper manufacturing process that's been used to make final products. And all these three types of focus are actually, if you are the same as I am from material science background, quite familiar with these three topics. So the property, structure, and process, they are the golden three pillars of material science because they are all interlinked. You change your property by changing the structure through the processing or other means. And if you change your processing, you're basically changing your structure. So among these three, structure is the most physical, the most direct. You can look at it directly. You look at the structure to understand the property and process a lot of times. So for structure, it's also just not by those three pillars, structure is important. If we look at the process of all additive manufacturing, structure exists throughout all the stages, from the design to the build to the processing and the final product. During the design phase, you're essentially making something from virtual to physical. You're designing a structure already. And during the build phase, you want to know if the build quality is good. You look at the structure to know if the build is turning out all right. During the processing, you want to see what the processing result does to your structure. And of course, for final product, you have to examine the structure to know if you did a good job. And one key thing about additive manufacturing pertaining to its fast iterative nature is that you are doing this process likely all over again and again. So you're porting your final product, the first version, back to design phase again. Now you're trying to port physical back to virtual. And to see if you did a good job modifying it at the build phase, you're also looking at the structure again to see if you have quality improvement. The same for processing. If the process modification actually improves, and the final product, you have to inspect it again. And this happens all the time. So as you see, you're always looking at structures. And not only that, because of so consistent looking at structure, you would like a type of structure analysis technique that gives you a very coherent integrated data format. Let's say if you have at one phase, your structure information is a couple numbers. The next phase is a graph. And the next phase is a couple curves. Well, you can definitely make a word, that's for sure, but wouldn't it be nice if you have a type of structured data that's all throughout and consistent? With that, I would say X-ray CT does a really good job on that. But before that, before introducing how good X-ray CT is for additive manufacturing, what exactly is X-ray CT? So from the name, you can probably guess it's a type of CT using X-ray as a light source. So CT is computed tomography. So usually you heard about the term maybe at a hospital for a medical use case. Like in this picture, a patient is about to go through a computed tomography scan. So after the scan, we would be able to get the 3D data of that patient virtually and then cut it open to see what's inside without actually cutting the patient open. And in the picture, you can kind of see, oh, I can see different faces, different structures inside with different kind of colors. There are some brighter areas, there are some darker areas. And with that is from the contrast of X-rays. So you see those pictures in different phases because you have contrast. So how do X-ray generate those contrasts for you? It's also very intuitive. It's because things absorb X-rays. Imagine you shine an X-ray on your topic, on your object. You have an incident X-rays coming to your object. After the thing absorbs some X-ray, you have a measure intensity of the X-ray, and you actually have an equation to express that kind of relation. And don't worry about the equation. I'm not going to ask you to plug any numbers in there today, so just bear with me. It's very intuitive. The T here just shows how thick your object is because it makes sense. If your object is thicker, it's probably going to absorb more X-rays. And the mu here is attenuation coefficient that's related to the material of your object. So it's also very intuitive to break it down that it tells you if your object is denser, higher atomic number, higher atomic mass, like lead or something, while you're using a lower energy X-ray to shine on it, you are expecting a lot more absorption. And this kind of absorption difference is how we get the contrast. So for example, here you shine an X-ray on different type of materials, from the heavy to the light ones. You can expect different contrast showing up at your detector or on your film. The same goes for the thickness of your sample, that you can see different contrasts based on how thick they are. So with that, we have the contrast, and then we have contrast between different phases. But how do we get more information out from X-ray CT? So an X-ray CT process will give you a 3D structural data. How to do that is when you shine an X-ray source on an object, usually if you just stop there, it's a regular radiograph. You have a 2D image. But if you do that throughout 360 degrees of your sample turning, you end up with a bunch of 2D radiographs. This process, collecting all these projections, is what we call scan when we're talking about CT scans. And with the advancement of computational power nowadays, it's really already very possible and very easy for you to have a PC powerful enough to handle the reconstruction of these 2D projections back into a 3D space to give you a 3D data of whatever you're scanning. So you can already probably have an idea of how good this will be for characterizing your structure. But obviously, X-ray CT is not the only structure characterization tool, right? How does it compare to all the other tools you probably would expect when you're doing additive manufacturing structure analysis? So what are the common structure analysis methods we use? There are some methods that's tried and true and very precise and very reliable, but they only give you very specific results, very specific feature analysis. For example, like Archimedes density testing tells you the density and only density. Or ultrasonic detection, it tells you there's a drastic change in phase, likely a crack or a void in there, and maybe how large it is. But can you see it? Can you tell where exactly it sits? Probably not. Also, coordinate measuring machine is very precise, tells you exactly some of the measurements, but can you see something inside the structure using this? Probably not. So I emphasize on seeing because seeing is believing. It's very intuitive for us to want to see what is going on, especially what's going on inside the structure we build. So we will want to rely on also image-based inspection tools. That gives us the microscopy, like either optical or electrical one, like SEM, scanning electron microscopy, or X-ray radiography, the 2D X-ray, like a medical X-ray you can expect, and obviously X-ray CT. So among these image-based inspections, how do you choose which one to use or which one to add to your arsenal? Well, we have to know what they can see. So based on different feature size, you probably want to choose different tools. And the key feature size we're interested in for additive manufacturing process lies about in these range. But when I talk about the size of the common AM features, I have to talk about what is the common AM features that people are interested about. And there's already quite a few articles summarizing these things because people already notice how useful X-ray CT is and how important additive manufacturing is. So there are some articles I would like to introduce here. And with that article, introduce some of the features. These articles are from Dr. Anton Duplessis. I encourage you to check the articles out, talking about some of the key analysis people do for structure analysis in additive manufacturing. First is powder analysis. Many of the 3D printing or additive manufacturing includes the powder. The powder quality affects how you print your product. So powder analysis is very popular. The second one is porosity analysis, because porosity can lead to cracks, lead to structure weak points. And for both powder and porosity, you often would like to know how they distribute and what's the shape of it. So you do some morphology analysis. Also, density analysis is a big thing. It's kind of related to the porosity analysis, but not exactly the same. As you can see in this picture, at the bottom of that sample, there are some, I would say, cave systems that's expanding from the surface inside the sample that will affect the density of your product. And the last one Dr. Anton Duplessis brought up was the surface roughness. Many of the printing processes leave you with some rough surface, could be caused by not very homogeneous fusing of the powders. So you want to look at the surface roughness. And I would like to also bring out another term that is very important for a lot of additive manufacturing, that is dimensioning. After all, you design it using CAD model, you want to know if you're printing out the exact same thing. So with that, you will want to do some tolerance variation analysis and actual to nominal comparison. And CT is very good for that, doing all these tasks I just mentioned. So why choose X-ray CT? Not only with the features I just bring out, let's also look at the process that's involved in additive manufacturing and how each of some of the imaging tools can help you. X-ray CT, by virtue of scanning your whole sample from the surface to the core, giving you a virtual clone, it helps you throughout from the build to the process to the final redesign, porting it back to virtual space. X-ray radiography, non-destructive, and seeing inside your structure can help you examine the product, but probably not giving you a 3D model to port back into redesign phase. SEM, very high resolution, gives you the best resolution of some of the small features like porosity inside. So it's good for build phase and processing phase. But because of the sample limitation, you're probably going to use SEM on your whole large product. For optical, it's also very useful throughout build, processing, and product phase if you look at the cross sections using optical microscope. And also, there are some optical techniques you can scan your final product and make a 3D model out of it, but it's limited only just to the external. So although they are both optical techniques, they are not really exactly the same. There's a discontinuation between them. So for the objective advantage to compare all these techniques, I would like to bring out is if there are some advantage that happens to possess or happens to be in one of the technique, it will just be better for your process or just better for your life, actually. For example, the internal structure information. We build the things from the scratch using AM. We want to know what's happening inside. So that cross out the optical method that only gives us the outside 3D model. We also would like it to be non-destructive most of the time, because although 3D printing, you might be able to spare a couple samples just to cut it open. If you do that, it always begs the question of if your cutting open process actually damaged something. You always will be wondering if there is a sampling bias. So that leaves us with two of the techniques here. And the difference between X-ray CT and X-ray radiography is the accessible spatial 3D data. Additive manufacturing, also known as 3D printing, we're building things in 3D. You definitely want to know about structure information in 3D. So that's why X-ray CT is very reliable and very useful for additive manufacturing throughout all different phases. Now, before I head into the next chapter, I would like to bring out the second polling question. And with that, I would like to hand it over to Angela.
Thanks, Ted. So I'd like to start launch our second and last poll question. Again, you can pick multiple answers in this case as well. So we'd like to know what additive manufacturing structural feature are you most interested in? Are you interested in analyzing the powder? Perhaps internal porosity? Is the density important to you? Or maybe even surface roughness? Or perhaps is dimensioning important to you? We have a lot of answers coming in really fast. 60% have answered so far. And again, Ted, it looks like we have a clear winner among this list. So I'm going to give 3 more seconds, 2, 1, and now I'm going to close in the poll and I'm going to share the results with you. And what we see is porosity is of most interest at 78%. That's large. And then followed by surface roughness at 54%. Powder analysis and dimensioning are tied for 41%. And density analysis is of interest as well to 35%. So thanks everyone for answering that question. And I'm going to stop sharing these results and send it back to you, Ted.
No surprise with that porosity.
Yeah. Thank you, Angela. And no surprise that those are all very interesting and very key features, like being categorized by Dr. Antoine Duplessis, right? So those are all very interesting aspects. And I'm happy to tell you, you will be able to see many of the examples covering all those interests that we just mentioned. So the next chapter, I'll be talking about some of the examples. But before that, I've been talking about introducing the additive manufacturing and also X-ray CT. I'm sure some of you will have some questions. So we can stop here briefly just to see if anyone has any questions so I can answer.
Yep, we have a question, Ted. You went through all the different types of additive manufacturing, which was really, really helpful in learning about the topic, right? But we talked about introduction to X-ray CT. Can one X-ray CT system or an instrument be capable of handling all different samples from different stages of additive manufacturing you mentioned, especially material type? Will different material type have any effects on how you scan the samples, metals versus powders and things like that?
Yeah, that's actually a really good question. So obviously, if you have a big, powerful CT system, you can put anything inside and scan it and have a scan result out, come out the other end. But to actually give you the most density of the information you're seeking, you want to optimize your scanning process. That's also tied to your material system, like you also asked. And for this example, like the metallic system, usually they're higher density, let's say comparing to a polymer system, right? So you will definitely want to use a different type of energy range and some different exposure setting, et cetera, et cetera. And that might be still sitting in the ballpark of the same equipment that you end up choosing, or it might not. You might actually have to consider what type of equipment you want to get to best suit your example, best suit your material. So yeah, so there are definitely some variations, and I'm actually going to show you some results from different types of CT that we have here later in the example session.
I guess it's that answer that everybody hates to hear, but it just really depends. That's really the best answer possible in this case. But obviously, with depending on the requirements, application, and material type, there are tools associated with them.
Yeah.
Yep.
Any other questions?
I think that was the only one for now. On to the examples that you wanted to share.
Okay. Yeah. If we have any new questions, just feel free to bring it out. We also have another Q&A session at the end. So yeah.
There's one that popped up. Oh, there's a couple that are popping up. Perhaps we can table those for later at the end of the presentation.
Okay. Yeah. So we can answer them together at the end of the Q&A at the end. Okay. Yeah. Thank you so much. And thank you everyone for being so involved with the presentation and everything. Yeah. Okay, so let's move on to look at the actual examples. That's a very most exciting part, in my opinion. So yeah, so for the structural analysis example, using X-ray CT of additive manufacture products. So let's go through a couple of them. The first one is of a photopolymer. It's manufactured using vapor polymerization. So as you can see here on the left, this is one of our equipment and one of our CT Lab HX is a very convenient benchtop system. And what I highlighted here is a sample stage with the photopolymer that's on the stage. It's something I printed. It's just a simple 2 cubes connected by a 5-cylinder at the center. And on the left, this is the cone beam X-ray source. And when the X-ray turns on, this is roughly how the X-ray shines, where we get our image. And this one, we have actually quite a good of a voxel resolution. Despite being a benchtop, a small profile benchtop, you have a highest voxel resolution of 2.1 micron. When you turn on the X-ray, what the detector sees is like this. If you just stop there, that's just a 2D radiograph. But granted, even with this, you're getting something already. You're seeing there seems to be something happening at the center pillar. There's maybe a gap, a void, but we don't have to guess. We can do a full 3D scan of it and then find out what is happening inside. So once we do a 360 scan, collecting all the projections and then reconstruct them into a 3D model, this is what we get. And with that, we can just slice that 3D model, or I should say a digital twin of our sample, and find out exactly what's happening at the center pillar here. As you can see, we are definitely having a lot more going on than just a simple gap. And with this, we have a lot more detail. Okay, there are different colors, there are definitely pores, there are different cracks. Like I just highlighted here, as you see, oh, those are the pores and the cracks. So with that scan, we can do even just 2D inspection is also going to give us a lot. So because we have 3D data, right? We can just slice it open at any place just to use it as a 2D image. So let's look at the center here. So because I know the printing process, the bad polymerization, and immediately I can tell because of the different contrast of the different faces inside from X-ray, I can tell, okay, so now I know, okay, these are definitely the wax that was used as a support for the internal structure, but they weren't leaked out properly. So after solidification, they shrink because they have different thermal expansion coefficient comparing to actual printing product. They shrink with the stress. There are pores happening. And what's surprising even to me here is the stress actually caused a crack that's growing into our printed material. It's not just limited to the wax. That's proper structural weak point, right? So we have a crack grew into the printed material. If I were to use this as a kind of like a stress condition, it might just crack and crumble from there. Now, we don't have to just stop at 2D inspection because now we have full 3D access. Let's say if I highlight all these pore areas because we have the contrast. In this case, the pore and the cracks are the darker or the darker peak. The left side peak you can see in a grayscale histogram. And let's highlight them and say we do this to the whole volume, throughout the whole volume, and then we can have a visualization of these cracks and pores inside this 3D printed product very easily and very intuitively, as you can see here. So already it's a very good 3D visualization tool to tell you exactly what's happening and where they're happening. We don't have to stop there. We can ask questions that's quantitative now. So for example, I know the void spaces is bad in terms of structural weak points, and I know the large ones are definitely bad news, but I don't know how small are the small ones are going to be an issue. So I can do some analysis and separate them and say, hey, ask questions like what's their aspect ratio? Because the more elongated or less spherical they are, there are more stress concentration points at the corner. With that, I can know more information on if I should worry about these smaller ones or just maybe address the larger ones. And also, aside from these kind of analysis, we can also do 3D dimensioning because now we have the essential a 3D clone of what we just made using additive manufacturing process. We're gonna ask questions like, hey, is this plane flat? Is there any weird bumps? Oh, is the radius or the diameter of the center pillar exactly as I designed? So you can do this dimensioning with this very visualized volume and maybe just do an overall nominal to actual comparison to see if there are areas that you didn't even pick up. So to do that, we overlap our CAD drawing model with our scan that we obtain. And would you look at that? We actually do have some nominal to actual deviation that we didn't notice. There's one pillar that's having positive deviation, meaning it's actually larger than design, and one pillar that's smaller than design. And that will cause some uneven load condition, right? So in this case, I learned about it because I did a nominal to actual comparison of the actual product I just made comparing to the design. On the right, you can see it's a 2D way to give you more idea if you feel like the 3D model is still not as intuitive or not easy to show. You had the full access to these kind of data. Now, moving on to the next example, because the first example is still quite large, right? You can see the size roughly. You may be asking, hey, what about powders? Can you image powders? They're quite small. In this case, I would like to show you the example of metal powder for powder bed fusion or direct energy deposition. In this case, we're using another of our CT equipment. Here is a Nano 3DX. It is a parallel beam system like this you can see here. So it's having a smaller range of field of view for you to image your sample, but it has a way higher resolution, in this case, the finest vascular resolution down to 325 nanometers. So what I'm imaging here is these titanium alloy powders you see on the left-hand side in the vial. And how I mounted it is I just put some glue on top of a pole and mix those powder in. So this is a good thing about X-ray contrast. Remember, the contrast comes from your material type. In this case, through the eyes of X-rays, those glues are essentially invisible. So those powders are as if they're floating in the air. So after scanning, this is what I get. You have those powders floating in the air, waiting for you to explore. And you can already see, oh, there are some agglomerations for some of the powders, some of the deviation to the sphere or the spherical shape they're supposed to have, some of them as if they're being punched in the center. You name it, you can do the analysis. In this case, I'm showcasing a mean fair diameter or some other analysis like the morphology, like the sphericity. And if these kind of 3D color coding information doesn't sit right with you, you want to see a bit more distribution in terms of 2D graphs like histogram, you also have it, because at this point, you have a full control of these 3D data. It's just in terms of how you want to show them, how you want to put them together to give you the most information. The next example is for a ceramic 3D printed sample. It's made using sheet lamination. It was scanned using the same Nano 3DX. And in here, you can see this is the green body, meaning it just got sheet laminated together with some of the process. So how I image it is basically I cut the tip of it and mount it onto the pole here again. And the bottom is really made just to support it. So the key is really that tip. And what we're seeing here on the left is like this. You can see clearly different layers of the sheet laminated together and some of the faces, secondary faces that's inside. And just for a comparison, this is one of the samples, sample A with certain composition. For another sample, that's sample B on the right side. You can see clearly the difference between them in terms of how the second phase is distributed and the existence of some of the cracks in one and a lack thereof in the other. And so here are 3D comparisons side by side for sample A and sample B, and with the slide-through view in the 3D to give you some connection back to the 2D image we just saw earlier. And also doing segmentation, highlighting those secondary area faces to showcase you how they distribute. And in some cases, in this case, you'll be like, oh, that looks a lot. This visually doesn't tell me a lot of things, but you have full control. So we can definitely do some filtering saying, hey, I'm just interested in the feature size in this range. Show me the distribution, in this case in 3D. And in this case, I would like to showcase some capability that CT, the non-destructive nature, offers you. This is the green body initially when it first was laminated together. So because it has to go through a certain processing before it reaches the final stage, we can look at how the structure developed throughout the process. So in this case, these three examples are separated. They're not really actual time resolved data with each other, but you can definitely do that with the non-destructive capability of CT. So in this case, I would like to show you the development of how potential time resolved analysis you can do for these type of examples. You can see from the green body to the brown body and the final center body, the modeling or the not as severe or not as clear anymore interfacial area. And obviously you can do the second phase analysis again with some more analysis information. In this case, I would like to know, oh, what's their equivalent spherical diameter, for example. Next example is a titanium alloy rod that's printed using powder bed fusion. And like pertaining to the previous question someone asked, actually is a very good question. We're switching to another CT because in this case, we know we're scanning something that's very dense, that's titanium alloy rods. So this CT system is a lot more powerful, a bit larger with a larger stage to accommodate larger sample, heavier sample as a whole. But still having a very good voxel resolution with the finest voxel resolution around 1.5 micron. So here are the two rods. You can even see the labels on them. One is D1, one is C1 for the different printing parameters. So this is how I mount them. So this is also a benefit for CT comparing to many other techniques. It's really easy to image it. There's not much sample preparation. I just mount it in a straw and then put it in there and then you can scan it. You don't have to worry about vacuum or anything else. So if we look from the top, this is the cross-section that we're seeing from the 3D data. You can already see some vacancies or gaps in there, and there are some powders probably not centered together well and trapped inside there. And we see from the side, you can see very clearly a layer that tells you what's the printing direction that it has gone through. Now, so a lot of inspection doesn't have to be pure 2D or pure 3D. You can benefit from both. For example, here on the left side, I'm slicing through, as you can see live, showing on the right is a corresponding 2D layer, 2D information, as if you're doing multiple SEM images. So in this case, you just have to do one scan. You have the full access to this information. You don't have to polish it every time you want to move on to the next surface. So here is just a movie showcasing the sample D1 of the section of that I scanned, how it looks like on the outside. The surface roughness seems to be quite rough. But what if we just kind of quantify to showcase you or visualize it better? So this is the surface roughness. I just compare the surface to a baseline, basically just a simple rectangle, and see how much it deviates from that rectangle. And also, porosity analysis that a lot of people are interested in. In this case, I separate them using different sphericity. You can already tell there's definitely a correlation between the more spherical, smaller pores at the corner and the more irregular ones that's pertaining to each layer that's being printed out. And this page is just a comparison, static comparison between sample D1 and C1. They're both printed using the same material, just different printing parameters. And again, if you don't like just the visualization of the 3D graphs, you have the distribution in 2D as well. And here is the porosity or void comparison. You can see there's definitely a very huge difference in terms of the porosity you're expecting using different printing parameters from D1 to C1. Now we're moving to the last example I'm going to showcase today. This is again a metallic sample. It's a superalloy, Inconel superalloy actually, using power bath fusion. So the example we have here, again, scanned using the larger X-ray CT, CP-Lab CP-Lab HV, sorry, we have here. And the sample here is a car. Well, it's not a real car, but it's a toy car printed using the Inconel superalloy. Again, the HV having a finest oxide resolution of 1.5 micron. So on the left is a immediately 3D render just to give you an idea what the car is looking like, and with some transparency to show you the internal structure. So it's not a solid piece. It is actually having some grid-like structures, as you can see here on the left and also on the right, using the 2D cross-sectional views. And if we just focus on the 2D cross-sectional views and zoom in, you can immediately tell, okay, there are some areas inside these grid-like structures that's having some irregular surface bumps, likely again not completely fused together powders, and the surface treatment after the printing can only address the outside of the car, right? So internal of the car is still like that. And then we can start asking some quantitative question like, if this car is to be subjected to some loads or some stress, how would the load distribute? Most likely it's going to be related to how thick each of the internal strut structures that you're looking at here is distributing, right? So I did a volume thickness analysis both in 2D on the right and 3D on the left. You can kind of have an idea of, okay, the thicker area is probably better at withstanding forces. The thinner area is probably not as good. But you have the control of the 3D model that you printed after you scan it. So why not just bring that 3D model directly back into the simulation that you're using? So before that, I would like to show you just a 3D visualization of the analysis that I just did. Just an overall grayscale rendering to show you the structure as well as the volume thickness, but in this time in a 3D fashion that I just showcased you earlier. So we're interested in the load distribution it might be subjected to, right? So let's just put it into an actual simulation and do a load distribution analysis to see how it goes. So in this case, I made a condition as if the car is being pressed evenly from the top of its ceiling, so with some force pressing against it. And then with the simulation, the outcome is here. This is the 3D stress distribution of the maximum principal stress. So the red means there's more tension, and the blue means there's more less tension or even some compression force. You can see already highlighted, there are some high tension area near the wheel of this toy car. So in this case, you can immediately answer a question like, okay, is this surpassing the material property of the inconel? Well, in this case, obviously it didn't. But with this, you will be able to modify the product, maybe increase the thickness, maybe change the distribution of the struts inside, and then you can move on to your next iteration that improves your additive manufacturing product. So here is, again, a 3D rendering of the surface that I rendered using the scan results, and then putting this surface render into the finite element simulation to simulate that force acting on the top of the car, like this green arrow, and then showcasing the maximum principal stress distribution in 3D, and with some nice rotation and some transparency to give you some view of different angles. And if it doesn't tell you a lot, because 3D can be a bit too much sometimes, you're always welcome to slice it open in 2D and get a look at the area you're interested in. So that's the last example, and we've been through a lot of examples, right? So let's go through a summary here. For all the examples I show, they are pertaining to different phases or different stages of additive manufacturing. So for example, the powder analysis is from the build phase. And through the build phase with exactly the same powder, I built it into the rods that's shown at the bottom with some surface roughness analysis and some porosity analysis. For the processing analysis, I compare the different stages of the 3D printed or laminated ceramics so that you can study the processing that you perform on your product. And for the final product inspection, both the fat polymerized model and also the car, they are final products. So you have a good inspection in that stage. And with redesigning, I was able to do a nominal to actual comparison and some dimensioning for the fat polarized model, and also for load distribution analysis, did a principal stress distribution analysis on the car model. So and then with those information, you'll be able to redesign your CAD drawing and then put it back into the 3D printer you're using, and then move on to the next iteration. And with that, I hope after this webinar, you've learned what is additive manufacturing in general and why structure analysis is vital to all additive manufacturing process and all additive manufacturing stages. What is exactly X-ray CT? What kind of information it provides you? And with those examples, give you a better idea on how X-ray CT can help you throughout the additive manufacturing process. And with that, we come into the final Q&A session so we can answer some of the questions you have, and feel free to bring out new questions at the stage 2. Yeah.
Thanks so much, Ted. That was excellent presentation. We do have some previous question that we tabled for at the end, and we have a new question. We can start with the initial ones first. I think you went over this as you were going through your application example, but one of the question was, what is the best resolution one can get in CT? And again, the answer is it depends, of course, but that was one of them. And then the second question was, for surface roughness, what are some software analysis would you suggest to obtain high Z materials like radium or cerium, like high density metals? I think if you can answer those two, and I'll have one more question at the end that I can share after.
So for the first question, like you said, there are different CT techniques that focusing on like giving you higher resolution or accommodating larger samples, for examples. So for the highest resolution, you're absolutely right. It kind of depends. I know that's a worse answer everyone expects, but in this case, that's true. But I can give you a ballpark. We usually say CT, the best resolution is sub-micron. So you're looking at a couple hundreds of nanometer. That's the highest resolution. So, but the good thing about CT is you have these 3D data at your disposal. You can correlate that with many other analysis techniques that can provide you with way higher resolution. In fact, that's what I did during my PhD research. I correlate a lot of SEM data with 3D CT data. So I use CT to pinpoint and know exactly where the places I'm interested in, and use SEM to give me way higher resolution at local area and correspond them back into the 3D space. So you can definitely do that. But for CT itself, to answer your question, I would say submicron, couple hundred nanometers is the most common when you're chasing the resolution. And the second question, Vero, you're asking the
High
audience
density materials. Yeah.
Yeah.
I think what he's trying to get at is the values of RA and SA, which are some measures of the roughness average. And I like what software or analysis packages can provide that. And you can correct me if I got that wrong in that question. Does VG do something like that?
From what I remember, not directly. I mean, like both VG Studio, as you remember throughout the samples I brought out, there are some logos at the corner. That means we're using different softwares. The ones I showed includes both VG Studio and Dragonfly. They're both very powerful tools, and the surface roughness example I showed, actually, I used Dragonfly. I would say Dragonfly is already quite powerful in terms of giving you some quantitative data in terms of the surface roughness. VG Studio definitely also has that capability, but they are more specialized in dimensioning and some of the porosity analysis and some very special case analysis and tool sets. Again, I know it's probably not the best answer you're seeking, but these tools are all very powerful and has its own strong suit. I encourage you just to explore more, because there are quite a few out there. But these two, I would say, is a good starting point, like VG Studio and then Dragonfly.
Yeah, you can output some of that quantitative information, the measures across. So then you can put that information into something else so you can calculate those averages and such. Yeah.
Thanks, Angela. I completely misunderstood that question.
It's okay. That's all right.
There is one more question. It's due to time required for micro CT imaging, are these type of analysis performed primarily as a forensic analysis during development or when something goes wrong? What are your thoughts there, Ted?
Yeah. So obviously, because you have to take a sample scan from all 360 degrees, so it's not as I would say it's not as used commonly for an inline inspection tool. Inline inspection, people usually use 2D radiographs more often. But the scan time can definitely be quite fast. I would say there are scans that you can perform just within tens of seconds. But it really boils down to what type of features you're looking at. For example, if you just want to look at if there's something missing, if there's a big crack in there, these kind of fast scan can already provide you the information. But if you're doing very thorough porosity analysis or very high resolution ones, for example, some people are interested in, usually that would tend to take you a longer time, maybe hour-long scan, or even if you're chasing really high resolution for some cases, couple hours long. So depending on your application, some of those numbers might already exceed the practicality that you can consider, but some of those might not. So again, it kind of depends, but really that's the answer. Yeah.
Got it. Thanks. And I think one more question I'd like to take is, aside from providing indirect feedback like dimensioning and simulation, when you showed the last example with the superalloy Inconel, is it possible to actively incorporate CT data to make a feedback loop for 3D printer to adjust the printing process?
Actually, that's a really good question, because CT actually has been used quite extensively in some industrial processings, and people have been doing exactly that, because since CT gives a virtual scan of your product and putting back directly into the digital space, there are softwares and programs out there that get that direct information and then translate that to the tweaking of your 3D printer parameters. Like, for example, because of various reasons, if you design your drawing like as is, it will always print it sideways or like a tilted certain degrees. And with that feedback, it can actually just adjust the printing process to correct for that. So there is softwares and services out there that does that.
That makes things a lot easier when you're in
Yeah.
the development process, right? So,
Yeah. Hey, Viral, I noticed someone asked Viral shared a lot of links today, and some were asking if someone could email. Turns out after this, there will be tomorrow a landing page, and that'll have all those links on there. So you can read for yourself some of these papers that Ted mentioned, or dive in a little deeper.
Yeah, there will be all the references and also the slides, the presentation slides I made, although there's a lot of animations I use, but there will be a static PDF version of the slides also ready for you to view all the time.
Yep, everything will be available on our website, as well as the recording of this webinar in your email. So you'll have access to all of these things. We do have a lot more questions, Ted, but I think some of these questions might be better off answered via email separately. Because I do want to take some time and move on to the last slide. Thank you everybody for joining us in our webinars in 2024. We love hearing feedback from our audience, and we would greatly appreciate if you can take a moment to fill out our survey on our webinars so we can continue to put out content that's relevant and interesting in the X-ray CT world. I'm going to share a link to the survey in the chat window where you can take a look at it. And if you can give us your feedback, we would greatly appreciate it. We're always looking for new ways, better ways to come up with new webinar content. So if you can take a moment and do this, we would really appreciate it. And that's all I want to say before we close off this webinar series. We have questions. We are aware of them, and we will follow up with those separately via email directly with the people that asked them. So thank you all for joining us today. Have a great holiday, and see you guys next year.
Bye, everyone.
Thank you.
Bye.